Prof from IST Austria, talking on linear programming and valued constraint satisfaction problem, and application k-submodular.
Okay, thank you very much. So is the microphone working? Okay. Yes, so I will talk about two topics, and both are about discrete optimization problems. So I'm roughly speaking, it's kind of map MRF inference problems. And the first question that I'll consider is which classes of discrete optimization problems are tractable. Well, there are some well-known classes such as so it's well known that submodular functions can be minimized in polynomial time, and this is very important for computer vision. For example, graph cuts is essentially a fast solver for special classes of submodular functions. So there are some other functions that can be minimized in polynomial time, such as bisubmodular functions, and they're closely related to so-called QPBO method. And what I would like to study is the following question. So are there any other tractable classes besides those two? And even better, can we actually give a complete characterization of such classes? And we'll see that actually, so we'll get the answer to this question quite soon. Okay, well, how do we formalize this problem? Well, so we will use the framework of so-called Valued Constraint Satisfaction Problems, or VCSPs. And it is defined as follows. So let D be some finite set of labels. For example, D can contain three labels, A, B, and C. Or in binary optimization problems, it would be two labels, 0 and 1. So a language gamma is just a set of cost functions over this domain. For example, a language gamma may contain two functions, G and H, where G is a function of just one variable, so it's a unary function, and H may be a function of three variables, for example. So that is one possible language. Okay, so given a language, we can now consider, we can now define a gamma, given a language gamma, we can define a gamma instance as follows. So this is an optimization problem where we want to minimize an objective function of the following form. So the objective function is the sum of functions from the language, and we have some set of variables, let's say in this case x1, x2, x3, and x4, and we can plug these variables in arbitrary places, well as the RITs match. For example, function h should accept three arguments because h is a function of three variables. Okay, so any language gamma defines a class of optimization problems, and now we can ask various questions about this class, and this class is called VCSP of gamma, and we can ask the various questions like what is the complexity of gamma? So is it, so can we minimize all gamma instances in polynomial time, or is it the problem SNP hard, or is it something in between? We can also ask other questions. For example, does a specific algorithm solve all instances, all gamma instances? For example, we can ask, does a certain LP relaxation solve gamma instances, and so on. And of course, the answer to these questions will depend on how rich language gamma is. For example, if gamma contains just unary functions, then it's easy to see that all gamma instances can be minimized in polynomial time. Well, we can easily optimize any sum of unary functions. But if we include some difficult function in gamma, for example, kind of not equal relation, then perhaps we can encode a kind of a coloring problem, and it would be NP hard if there are more than two labels. Okay, and so once again, we'll focus on the following language. So given a specific language gamma, we want to understand what is the complexity of gamma. Well, and I will distinguish between three types of VCSPs. Well, the first class is plain CSPs, plain constraint satisfaction problems, and this is the case when all functions take either value 0 or infinity. And this corresponds to a purely feasibility pure feasibility problem. So given an instance, we are interested whether there exists at least one feasible solution. So we can also consider the case of finite valued CSPs, where all functions take some rational values, and then it's a pure optimization problem. And we can also consider general value CSPs, which combines these two cases, and this kind of combines feasibility and optimization problems. Okay, so there are these three possible types of VCSPs, and let me make one remark. So if we have some general valued CSP, we can also consider a corresponding CSP by taking each function and replacing each finite valued value with a 0. And the new language obtained in this way will be called phys of gamma. So I will use this phys of gamma a bit later in the talk. Okay, so first let's consider this first case, plain CSPs. So what is known about this case? Well, there is a famous conjecture by Feder and Vardy, which states, so they conjecture that I is the CSP language is either tractable or NP-hard. And there is actually a refined conjecture by Bulatov, Johan, and Krokhin, who actually conjectured a specific condition which separates these two cases. Well, there has been a lot of progress on this conjecture, and the picture looks like this. So this is the class of all CSPs, and this is the boundary given by this condition of Bulatov, Johan, and Krokhin. And actually, it has been proven that all languages here are NP-hard, and so there are many partial kind of results for this case, and actually, yeah. So there are lots of different results. So what can we say about the general case? Well, actually, it turned out that earlier this year, 3 papers appeared on Archive which claimed the solution to this conjecture. So actually, well, it turned out, so the first paper has been retracted, but I saw that the 2 other papers has been accepted to Fox. So presumably, we can assume that the dichotomy conjecture has been resolved now, and the picture looks like this. And we know kind of the exact boundary separating these 2 cases. Okay, now let's move to finite valued CSPs. Well, the full dichotomy for this case has been obtained a few years ago, and in particular we have the following theorem. So suppose that language gamma admits a binary symmetric fractional polymorphism. So this is some technical condition which I will explain in the next few slides. Okay, so if this condition is satisfied, then all gamma instances can be solved in polynomial time, and the algorithm for doing this is just a certain linear programming is to solve a certain linear programming relaxation called the basic LP. So this is a very natural relaxation. I will not describe how it looks like, but yeah, it's quite popular. In particular, it's used a lot for map MRF inference problems. Okay, so and this has been shown by Thapper, Zivny, and myself. And Thapper and Zivny also showed that if this condition is not satisfied, then language gamma is NP-hard, and together these 2 theorems give a full dichotomy for finite valued languages. Okay, so next I'm going to explain what this condition means, and I'll start with a special case. I'll start with submodular functions. Okay, so imagine that we have some function of 6 variables, and each variable can take 5 possible labels, right? So function f is called the submodular if it satisfies this. Yes, and we assume that all these labels are ordered sets, is an ordered set, is a totally ordered set. Okay, so the function f is called submodular if it satisfies this inequality for all possible labelings x and y, where this operation is component-wise minimum and this operation is component-wise maximum. Well, this is some illustration of this condition. Suppose that the red line represents labeling x, the blue line is labeling y. So when we take the component twice minimum, we obtain this labeling here. When we obtain component twice maximum, we obtain this labeling here. And this condition says that the combined costs of these dotted labelings should be smaller or equal than the combined cost of the blue and red labelings. And this should hold for all possible choices of red and blue labelings. So roughly speaking, this is kind of some kind of smoothness assumption on function f. Well, that's one way to look at this. Okay, so these are submodular functions, and now I will define a larger class of functions. So I will consider all functions. Suppose that all functions in a language satisfy this condition here for all labelings x and y, where this symbol denotes an arbitrary symmetric operation, and this operation is applied component-wise. So omega is some probability distribution over such symmetric operations. So if there exists such probability distribution omega so that this condition holds for all functions in the language, then this theorem will apply, and then we'll know that LP relaxation will solve the problem. And otherwise, if such omega does not exist, then the language is NP-hard. And note that the case of submodular function is a special case of this. It corresponds to the case when we put when the probability distribution omega puts 1/2 on the max operation and 1/2 on the mean operation. But this allows kind of to more general classes, so yeah, it can be an arbitrary probability distribution over symmetric operations. Okay, so this was the case of finite valued languages. Now let's move to the general case. So what can we say about this case? Well, so Kozik and Echremyak provided a necessary condition for tractability, which is a bit technical and it's not really important. But so what they showed is if this condition does not hold, then the language is NP-hard. So what we did, we showed the following result. So suppose that let's take some arbitrary general valued language gamma, and suppose that the Kozik-Echremyak condition holds, and suppose also that the language, this phase of gamma is also tractable. Then we proved that in these cases gamma is NP-hard, and we give a specific algorithm for solving these kind of problems, which I will describe next. And if these two conditions do not hold, then actually now, since we now know that the dichotomy for CSPs hold, actually we can now conclude that the dichotomy for VCSPs holds, and now we have a general kind of classification for arbitrary general valued CSPs. Okay, so let me briefly describe how we achieved this result. In other words, what is the algorithm for solving languages that satisfy this condition? Well, and the algorithm is actually quite simple. So suppose that this is our input function. It is defined on 3 variables, and each variable can take 3 possible labels. So first, what we do we do some CSP preprocessing. So let's say we pick this label, and we ask the question: does there exist at least one label, feasible solution which takes this label? If the answer is no, then we cross it out, otherwise we keep it. Yes, and we do this for all possible labels, and we can do it in polynomial time because we assumed that the problem phase of gamma is tractable. So we just kind of call the oracle for solving the language phase of gamma. Okay, so this is the first step. And the second step, we just solve LP relaxation of this modified instance where we removed all these bad labels. And kind of the main result that we obtained is that if the condition of Kozik-Archimedes holds, then then solving this relaxation will always give kind of the exact result. So this relaxation will always be tight. Okay, so this concludes the first part of my talk. So to summarize, so kind of we now have kind of a full dichotomy for valued constraint satisfaction problems, and now we can ask: are there some interesting classes, interesting tractable classes that are useful for computer vision? And this will be the second part of my talk. Okay, so what are interesting classes? Well, one class is submodular functions, which I already mentioned. There are also bi-submodular functions, and they are useful for obtaining partially optimal solutions for optimization problems with Boolean variables. So what I will talk about is the so-called k-submodular functions that we introduced together with Anna Huber. And I will show that this class of functions can be useful for obtaining partially optimal solution of general discrete optimization problems. And and in this talk, actually, I will focus on the problem of obtaining a partially optimal solution for Potts energy functions. Okay, what is the Potts model? Well, probably most of you know this. So yeah, so we have some set of labels. So let's say each pixel can take k possible labels, and the Potts function has arbitrary unary terms plus these pairwise terms where lambda pq are non-negative constants. Well, of course, this problem is known to be NP-hard if there are 3 or more labels, but there are some efficient approximation algorithms. For example, there is a famous self-expansion algorithm which gives a true approximation. So since this problem is NP-hard, we will not try to solve it exactly. Instead, we will try to obtain a part of an optimal solution. Well, so we'll be interested in partial optimality. What does it mean? Well, so a partial labeling is just some labeling of a subset of nodes. For example, this region is labeled and this red region is unlabeled. And we say that the partial labeling is optimal if it can be extended to an optimal solution of the whole function. Okay, so how can we obtain partially optimal solutions? Well, we can use the k-submodular relaxations for this purpose. So how does this work? Well, suppose that we have some arbitrary function f, which can be NP-hard, for example, it can be Potts model. So what we can do, suppose that this function was defined, the set of labels contained the 4 possible labels, which I illustrated here. So first, let's introduce a new red label, which will correspond to the unlabeled status. And now we will be looking at functions over this extended domain. Okay, so now given function f, let's construct a function g over this extended domain, which is an extension of function f. In other words, it coincides with f on the original set of labels. And we will also require that function g is k-submodular. I will define next what it means. And if we do this, and if we later minimize function g, then there is a two-line proof that the minimizer of g will be a partially optimal solution for the original function f. So that's the general strategy that we'll use. Okay, well, now let me define what is a k-submodular function. Well, function g over this extended domain is called k-submodular if it satisfies this inequality for all possible labelings x and y. Okay, and now we need to define these two operations, which I'll call AND and OR, and these two operations are defined as follows. Okay, so we need to define the result for any pairs of labels A and B. Okay, so if A and B both belong, let's say, to this set of labels, then the result will be mean and max. And this means that if, and this is kind of similar to the case of submodular functions. And this means that if we restrict a k-submodular function just to this set of labels, then we'll obtain a submodular function. Okay, and if A and B are different labels, which are also different from this bottom label, then the result of both operations will be this extra label bottom. So this is how I define these two operations AND and OR, and this gives a definition of k-submodular functions. Okay, so what is known about k-submodular relaxations? Well, in an earlier paper I considered the case when k equals 2, and in that case we obtain so-called bisubmodular relaxations, and I showed that bisubmodular relaxations characterize extensions of the so-called KPBO method. The case of when k is more than 2, so this case has also been considered. In particular, Thapper and Zivny proved that an arbitrary a k-submodular function with pairwise terms can be solved by LP relaxation. Together with Igor Gridchyn, we proposed an efficient method for minimizing k-submodular relaxations of the Potts energies. So that's what I will describe next. Then there was some other work by Vata, Wallström, and Yoshida, who, for example, showed that some k-submodular functions can be reduced to a max flow problem. And the equation of constructing k-submodular relaxations is addressed in this paper. Okay, so there has been some work on k-submodular relaxations. So what I will do, I will describe this work. Okay, so let's consider Potts energy, and now let's. So first, we need to define somehow a k-submodular relaxation of a Potts energy. So just to remind you, this was the original function. It's the sum of arbitrary unary terms and the sum of pairwise terms of this form. So a k-submodular relaxation that we will construct will have the following form. So it will have some unary terms, plus for each original pairwise term we define a new pairwise term, so this will be a relaxation of this. So what is this function d here? Well, the function d will be a tree, so it's so-called tree metric. So in other words, d of a, b is just the distance from label A to label B in this tree, where the length of each edge is 1/2. For example, the distance from here to here is 1, 1/2 plus 1/2, and this coincides with the value of the original term for labels A and B. So if the A and B are distinct labels here, then this term equals 1, well, lambda ij. And if A and B are the same label, then the distance between them is 0, and again it agrees with our original term. So in other words, this is indeed, so this pairwise term is indeed a relaxation of the original Potts term, and it's not too difficult to check that this tree metric is a k-submodular function. Well, we also need to define we also need to construct these terms G, these unary terms somehow. And well, okay, so this term, this unary term G should be an extension of the original term Fi. And this means that we know the values of Gi for original labels. And it remains to assign some value for the new label. So some cost for the new label. Well, so what we do, we assign the highest possible cost to this label so that this unary term remains k-submodular. And it's not too difficult to check that we need to use the following rule. So we pick the two smallest costs among the original costs, in this case 0 and 3, and we take the average, and this would be the cost here. Okay, so I defined how we construct the k-submodular relaxation of Potts energy, and now we need to minimize this function somehow. So we need to minimize a function of this form. And what we showed is that this function can be minimized via log k max flow computations, where k is the number of labels. Well, at this point, I need to make one remark. Actually, there have been early approaches for obtaining partially optimal solutions. In particular, there is an approach by Kofton, and it turns out that the approach of Kofton is stronger than k-submodular relaxations for the case of Potts energies. But it turns out, so we showed that the approach by Kofton can be solved by the same approach. So the optimization problem here can be cast as the problem of optimizing this objective function. And therefore, our work kind of gives a method for solving relaxation here using log k max flow computations. And originally, Kofton proposed to use k max flow computations. So we speed up this method. Okay, but actually it's a bit it takes some time to explain what is the Kofton method. So for simplicity, I will focus just on k-submodular relaxation. Okay, so next I will focus on the problem of minimizing this objective function. And we'll see how we can do it using log k max flow computations. Actually, we'll consider a slightly more general problem where our tree can be an arbitrary. So now we assume that each variable takes values in some space of labels, and this set forms a tree, and this function here is just the tree metric in this tree. Okay, so we build on the work of Felton, Schwab, and colleagues, who proposed an efficient method for minimizing this kind of functions in the case when unary terms have a special form. In particular, they assume that for each variable there is some special node, special label Ci, and the unary term is just the distance between label Xi and this special label Ci. So these Ci's are fixed. Well, in our so in our case, actually, we need the more general unary terms, and so what we do, we extend the method to more general unary terms, and we also give a new proof of correctness of this method. And this new proof of correctness was kind of essential for proving that this whole thing works. Okay, well, before describing the method, let me actually mention one special case, and this is the case when this tree is just a chain, right? So each variable can take labels from this set. And in this case, the distance from here to here is just the total variation potential function, right? So it's just the absolute value xj minus xi. And in this case, so it has been known, so it's been known that if the unary functions are convex unary terms, then this problem can be reduced to a parametric max flow problem and solved by divide and conquer algorithm, and this is due to Hochbaum. So essentially, we kind of extend this idea to more general trees, not just chains. Okay, but for this approach to work, we need some condition on the unary functions gi. So in the case of chains, this condition was the convexity. For more general trees, we need some generalization of this, and what we do, we just essentially we require convexity for any for any pair of adjacent edges. So okay, we need convexity along any path in this tree. So that's what we need, and we also can allow different edges to have different length. And so what we need, so if we take, let's say, any three labels, consecutive labels, let's say A, B, and C, so we need this cost to be the cost of label B to be below this line. Yeah. So that's the condition. And we say that unary functions that satisfy these conditions will be called the T convex, where T is this tree. Okay, and so yeah, we give a divide and conquer algorithm for functions with T convex unary terms, and the algorithm works as follows. Okay, so suppose that we want to minimize this function. So what we do, we pick some edge AB in this tree, for example, this edge, and we minimize this the function, and while restricting the set of labels just to these labels. Well, this problem kind of can be solved via graph cuts, via max flow algorithm, and suppose that the graph cuts gives this solution. So this is the optimal solution for this problem. Well, okay, so actually the projector doesn't show this for some reason, but in this case we have a guarantee that the original problem has an optimal solution, so that for these two variables the optimal solution lies here, and for these three variables the optimal solution lies here. And this means that we can use a divide and conquer approach. Now we can consider two independent subproblems, where for this subproblem we restrict the set of labels to this subtree, and for this subproblem we restrict the problem to this subtree. Yeah, and we just solve these two subproblems using the same approach. Yes, so that's the algorithm. There is actually one problem when we apply this approach to these star-shaped graphs, and we need these graphs when dealing with the pots, with k-submodular relaxations of pots of the pots model. So, and the problem is that if we pick any edge in this tree and we do a split based on this tree, then the problem will decompose, but the decomposition will be very unbalanced. So one of the problems will have, let's say, k-1 labels. Well, to deal with this problem, we follow the approach of Felsenschwab and colleagues. So what we do, we insert a new edge here, where the length of this edge is infinitesimally small, and if it is very small, then basically this change does not change the problem, essentially. And now we can do the split along this edge, and now we get a balanced split. Okay, so let me illustrate kind of a possible run of this algorithm in the case when, for POTS model, in the case when we have 7 labels. So this is our set of possible set of labels. So there are one root node and 7 leaves. Okay, so first we pick some partitioning of the nodes. Let's say we insert this edge, so and this partitions the nodes into labels 1, 2, 3, 4, and 5, 6, 7. Then we run the max flow algorithm, and then we get to regions. And now we know that this region is guaranteed to be labeled with one of these 4 labels or the root label. And this region is guaranteed to be labeled with this with these labels or with this label. Yeah, and we just keep doing this recursively, and we obtain at some point we obtain kind of this labeling of the image, which we call the Kofton labeling, and then there is we do one extra max flow, and it gives us some set of unlabeled nodes, and this is the optimal solution to this this is the minimizer of this k-submodular relaxation. And what we can do now, we can run another algorithm for this unlabeled part. For example, we can run the alpha expansion algorithm. And if there are fewer unlabeled pixels, then this can be much faster. Yes, and one can show that all these computations take log k max flows. Okay, these are some results. Okay, so we ran it on a stereo problem. So we used for computing unary terms, we used aggregation with 9x9 windows. And on average, so we obtained kind of 50 from 50% of 50 or 90 up to 93 fraction of pixels were labeled, and this is consistent actually with the Kofton's implementation, with the Kofton's paper. Yes, and so once we obtain a part of an optimal solution, then we can use alpha expansion just for the unlabeled part, and this is actually what the reuse and recycle approach of Alahari does. And we also observed that if we use a Kofton's labeling as an initialization for the alpha expansion approach, then this speeds alpha expansion a bit. Okay. And by the way, the computation time for this for our method is just a fraction of time of the alpha expansion runtime. So I would argue that this should always be a preprocessing step. Okay, so to summarize, so in the first part I presented kind of dichotomy classification for general valued constraint satisfaction problems. So now we have a full picture of which VCSPs are tractable and which VCSPs are not tractable. And in the second part, I considered k-submodular functions, and I showed that they can be used for obtaining partially optimal solution, in particular for POTS model. And yes, as the last slide, I'd like to mention that I'm based at Institute of Science and Technology, Austria. So this is a fast-growing institution, and we have positions at open positions at all levels. And in particular, if you're interested in my group, please contact me. Okay. Thank you.
Okay, thanks very much. And there's plenty of time for questions.
So the labels have to be partially ordered all the time. Is that an important assumption somewhere?
Well, for the POTS model, the labels, there is no order on the labels, right?
Except for, well, I guess you have.
Well, when we add this special label, yes, then we kind of introduce an order that this label should be lower than all other. This new label will be lower than all other labels, but the original set of labels is unordered.
Just when you defined your, like, before k-submodularity, I forgot what was the condition's name, but it seemed like you needed a pairwise minimum for all labels, and then you started talking about trees. I got lost somewhere where this transition happened from being able to define pointwise minima to some kind of tree metrics or something.
Okay, so we have, let's say, we've taken Potts model with arbitrary unary terms and pairwise terms of this form, right? And okay, let's look at unary terms. For example, so the unary terms can be arbitrary. For example, for this label, the unary cost is 3. For this label, the unary cost is 4, and so on. So they're arbitrary. Okay, now we want to define a k-submodular relaxation of this unary term. So what we do, we introduce a new label, and now we need to assign some cost to this label. Well, and actually, we would like this cost to be as high as possible, because when we minimize this function, we want to avoid kind of unlabeled solutions. Therefore, if this cost is high, then we will be avoiding this cost. But we cannot. I mean, we can set it. We cannot set it arbitrarily high. As the function must remain k-submodular. And it's easy to find the condition for the maximum possible value of this function, so that this whole function remains k-submodular. So what we need to do, we need to look at the original costs, pick the two smallest values, in this case 0 and 3, and take the average. Does this?
I'll take I'll take it offline. I still want to ask you something.
Any more questions?